Greet, greeting from Texas A&M University. My name is Steve Su. I'm honored to be given this opportunity to share with you some of my thoughts on controlling nonlinear systems. Allow me to start my talk with a very typical example that we all exposed to when we first took the vibrations, if not in undergrad, but definitely in graduate program. So here we have a pendulum, and then using Lagrangians, we can derive the governing equations as such, and then through assuming small angle assumptions, the governing equation can be simplified, linearized to be look as the second equation at the bottom. So essentially is when the theta is the sweeping angle is small, then sine theta can be replaced, or supposedly can be replaced with theta. At least this is considered as mathematically rigorous. These two figures, the one on top shows when the initial angle is 5 degrees. The one below when the initial angle is 2 degrees. They're both considered small. Okay, and this time domain response of the both the nonlinear pendulum as well as the linearized pendulum, they were overlapped on top of each other for comparison. And then as we can see that the time domain histories or responses in terms of the errors are initially small. But however, as the system progresses, the time error rapidly grows with prominent growing phase lags between the two models. Okay, and then this discrepancy becomes even more severe if the system is allowed to evolve, to progress even further. And then with the significant prominent phase lag, that certainly indicates the difference in terms of the frequency content, spectral response. And indeed, for linearized pendulum, there is a definitive fundamental period, which is not a function of theta. But however, for the nonlinear pendulum, the period, or in other words, the frequency is a function of the initial condition theta I. Okay, this necessarily implies that the system does not have a definitive oscillation frequency. Okay, indeed, the frequency is time variant. It depends on theta. Because the spectral compositions is considered the fundamental signature of any dynamic system, the linearized pendulum is physically and then characteristically a different system from the nonlinear pendulum. Controllers derived from linearized model therefore must compensate the linearization error at a huge cost, including at expenses of more power, compromised performance, and as well as system instability. Let me make it a few arguments out of those observations that we made with the linear and nonlinear pendulums. Linearization distorts and misinterprets true dynamics. The moment Taylor's expansions is employed, stationary dynamics is assumed. Eigenvectors, they're the mutually orthogonal So they are basis function that span the solution domain of a linear system, where the mapping is linear. However, nonlinear systems do not have characteristic eigenvectors because mapping is not linear. Stability study using eigenvalues is therefore only applicable to linear systems. Contemporary control theory share the following. They usually engage in linearization. Most, if not all of them, ignore time frequency coupling. They also employ feedback, and they also make assumptions to make the solution process easier. The issue with linearization was linearization, as we saw with the example on pendulum, distorts the genuine characteristic of nonlinear dynamics. And plus, linearized system is not able to resolve root to chaos. The second thing is, we all know that through the possible theorem, right? Time and frequency and time, they're coupled. Okay, they're the same side of they're the two sides of the same coin. And then plus, later on, I'm going to use several examples to show you that for a chaotic system, the frequency response are unstable as well as broadband. Employing feedback, because nonlinear system, they're all highly sensitive to the initial conditions. So with the feedback, essentially to provide a system with ever-changing different initial conditions for each and every control loop. Okay, and that serves to perturb the system. And then oftentimes, as well, I'm going to use an example to demonstrate this point later on. With the feedback feature implemented, then the systems actually tends to behave in a way that at the minimum instability, at the worst is it tends to show something that is aphysical. The assumptions, oftentimes there is all kinds of assumptions were made. The most prominent one was assuming that root to chaos process is non-stationary. But however, in true the physical system, root to chaos is non-stationary. Let me use an example to show you some of the fundamental features of a perturbed chaotic system, non-linear system. What we're seeing here is on the left is the instantaneous frequency of a cracked rotor. This rotor has a transverse crack. As the rotors spin, the crack gets to be open and close, open and close. So this crack breathing process necessarily perturb the dynamics of the rotor. Okay, and then this instantaneous frequency plot shows the horizontal axis as time, vertical axis as frequency. It shows that the system has bifurcated at one point already, and it's on its way to chaos. At this current stage, right around 1.8 seconds, okay, before this low frequency mode was born, the two existing mode undergoes a transitions, okay, undergo a change of what I call a temporal modal structure. The reason that I named it so, temporal modal structure, because as you can see, the frequency, the highest mode does not stay at a constant frequency. The frequency actually varies slightly above and below a fixed frequency around 100 hertz. Okay, but then as the system become bifurcated at that instance, this high frequency mode take up a different temporal modal structures. Okay, as you can see that the range of this oscillating frequency is actually larger now. Okay, and the same observations is also made with the second mode. Okay, and this second mode also experience a change of the temporal modal structures. And so these are the fundamental characteristics associated with a system that's undergoing instability on its way to chaos. As the dynamic deteriorates even further, then we're seeing more lower frequency mode was born. Okay, and then accompanied by a rather prominent, significant changes of temporal modal structure of those existing modes. This is when deteriorations got even worse than the previous. And what you can see is if we take a projections of the frequency to the left, then we can see that the frequency spectrum not just get to be wider, but also the frequency content changes as well as a function of time. Okay, so that was the preliminary observation when a system is undergoing bifurcations and becomes unstable. Okay, let me give a quick review of more than a dozen modern day control theories. The first one is probably the most known is OGY method. OGY perturbs a discontinuous parameter. It forces a trajectory to follow a target UBO in a chaotic attractor. And then OGY method use eigenvalue of the system's Jacobian at fixed point to establish stability. Okay, let me sidetrack just a little bit and then use this slide to point out that Jacobians, which employs Taylor theory, is actually a multidimensional linearization, as we can see, with only the linear terms in the equation being retained. This example is on applying OGY method to the control of a Hannon map. Okay, the figures on the left, it shows the Hannon map, the bifurcation plot of the Hannon map without the OGY control applied. The one on the right is when OGY controller is applied. Okay, but then this controller is only effective to certain point, and then beyond that, the systems becomes unstable. This dynamic instability rather abruptly becomes highly unstable. This instability level is extreme. Okay, so this OGY method, which is based on Jacobian, can only be applied to the proximity of a predetermined fixed point. Second one that I would like to review is Lyapunov-based control. And Lyapunov required the design of a control law, right, based on heuristic method. Now this is an example, the example on applying Lyapunov-based control to the two Duffing oscillators. Okay, we we consider two Duffing oscillators, with the second one has a forcing term, which is non-stationary. Okay, so apply Lyapunov-based control to the stationary model and also to the non-stationary model. And you can see that from the two corresponding instant frequency, Lyapunov-based control worked well. However, from this graph right here, we can see that when the model is non-stationary, Lyapunov-based control basically breaks down. Okay, and we see that there is all the frequency modes becomes highly unstable, and it becomes progressively more broadband. And then I would also like to make a comment when it comes to the Lyapunov-based control. The control law usually neither intuitive nor lending themselves to sound physical interpretations. And then quick review, there is also a PID control that is quite common. Those are most commonly the applications. Also the adaptive PID control, physiologic control, model reference adaptive control, feedback linearization control, time delay feedback control, Takagi-Fuzzy control, sliding mode control. This is the control methodology that's gained very wide popularity in the last few years. The issues with it is there is always chattering. Okay, chattering indicates instability, indicates high frequency. It has all kinds of negative impact on control stability and also robustness. Adaptive control and back stepping control. There are several issues with this particular control methodology. Is control design is tedious, and also the control law oftentimes is too involved to be practical. Okay, let me summarize as to those observations, the review that we made with the last dozen slides or so. All reviewed the control theory. They fail to mitigate dynamic chaos. A priori knowledge of the system needs to be available for the control theory to be effective. And none control both time and frequency response simultaneously. So about 15 years ago, I wanted to be able to formulate a novel control theory that addresses and retains the fundamental characteristic inherent of all nonlinear systems undergoing root to chaos. A theory that requires no linearizations or closed form solution, so that the genuine underlying features of the system being considered are preserved. And the theory also needs to be able to restrain time varying frequency spectrum from becoming broadband, and also be able to identify the dynamic state of the system in real time. And lastly, the theory also need to be able to facilitate control in the time frequency domain simultaneously without distorting or misinterpreting the underlying true dynamics. So at that point in time, I developed a task plan with the several tasks identified and defined. The first one is to investigate root to chaos in time and frequency domain concurrently, to identify the essential elements of nonlinear control through studying the inherent property of bifurcation and chaos. Of course, these are at essence fundamental to being able to develop a nonlinear control theory that requires no linearization and closed form solution, of course. And how do I facilitate simultaneous time frequency control through accessing wavelet transform. Okay, right here on this slide, it shows the bifurcation plot of a single weld non-stationary Duffing oscillator. Okay, there is 4 regions identified, A, B, C, D, and then at the bottom there is 4 instantaneous frequency plots associated with each regions. As you can see, at A has one single mode with very well defined temporal modal structures. Okay, with this frequency seemingly oscillating following a specific period in time. And then as the systems become further bifurcated into B and C, what we see is we have now more modes showing the more sophisticated temporal modal structures. And then as we reach into region D, the overall Duffing oscillators system response is actually become broadband. Okay, so now let me summarize my solution philosophy. Based on all those the observation we made with regard to the property of nonlinear response. Okay. The first one is a nonlinear system is highly sensitive to initial condition and time delay. This implies the use of feed-forward concept, feed-forward control concept. And then I took inspiration from adaptive filter. The second property is deteriorations in both time and frequency domain. When the dynamic system become unstable, it is on its take up a route to chaos, then the deterioration is actually in both time and frequency domain. This implies the need for addressing both time and frequency responses, all right, at the same time. And I took inspirations from discrete wavelet transform. The last property is a route to chaos is time dependent. The entire process is non-stationary. This implies the need for online identification. Okay, if proper control is to be secured, it be realized. And I took inspirations from modern day adaptive control. Okay, let me give you a top level overview of this nonlinear Wavelet-based nonlinear time frequency control theory that I developed. And this theory also has a powerful feature, and I call that feature local adaptability. Let me use this figure to show the basic concept, the basic architecture of this control theory. In essence, this control utilize FX LMS algorithm, okay, to facilitate online system identifications and also control. And these 2 boxes labeled with capital T or 3, these are wavelet, discrete wavelet transform. Okay, so simply put, and the input to the nonlinear system is run through wavelet transform before it got modified, redefined by using filter W2 and W1 hat. W1 hat is the same as W1, and this W1 on this component which is for online system identification, is for identifying systems response. And then the filter is updated based on errors. Based on the errors, that means errors established with establishing with a desired output. Okay, and through the application, the use of wavelet transform, so a time domain sequence or signals is decomposed into wavelet coefficients, and then wavelet coefficients, they carry both time and frequency information, and that's the wavelet coefficients that got processed. That was processed to establish system identification as well as system control. And to update filter W1 and W2, we need to pay attention to this optimization step size, mu1 for W1, mu2 for W2. Okay, and as you can see that from this steepest descent algorithm for updating the filter coefficient, mu1, which is the optimization step, is important in the sense that it essentially determines as to the convergence speed, as to the solutions and stability. So if mu1 was not properly chosen, then it may not be easy to have converged solutions, and then the system could easily become unstable. And then through a rather meticulous iterations, we found that mu1, okay, mu1 can be updated at each and every control step using this simple criteria. Same thing with mu2, which is used for updating W2 filter for facilitating controlling input. And then through a very meticulous derivations, the entire derivations took about 126 equations to eventually allows us to arrive at this right here, which is establish the criterion for setting up the optimal step size for mu2 for updating the filter W2. Okay, and then mu1 and mu2, they are both updated at each and every control step. So that's why I named it both our control theories as one that with local adaptability. And then the use of proper mu1 and mu2 ensures the stability and the fast conversions of the controller. And also because we're dealing with control theory is for controlling nonlinear system. So it's also very important that we get the W1 filter coefficients and the W2 filter coefficients right for the first guess in terms of the initial conditions. Okay. We also, through a rather meticulous, comprehensive derivation, we also have a way to show that what would be the optimal, the proper initial guess for W1 filter coefficient as well as W2. Okay. And now it's time to apply the control theory to a few applications to demonstrate as to the viability of this control theory. The first one we consider is the grazing control of a vibro-Impact oscillator. As the name grazing indicates that this is a discontinuous system, okay, and then grazing is as a sophisticated, rather involved discontinuous dynamics is very difficult to control. All right. So now this is the model that we use with the Heaviside functions defined as such. All right. So essentially, this is a card got driven by a harmonic input, and then this card without a controller would run into and make an impact with this with the wall on the right. And then through the proper use of X0, so we get to normalize and then turn the space variables into dimensionless terms, and then so the entire governing equation now looks like this with dimensionless state variables. And now using this table right here to replace alpha, omega, eta, and all that with those numbers, and then we did a simulation. What we're seeing here is the phase plot of of this oscillator. As you can see that the entire response is highly discontinuous, okay, highly nonlinear. And as also tested the same is the instantaneous frequency plot on the right. There's many different modes, okay, with very sophisticated, intriguing temporal modal structures, all present. And from the instantaneous frequency is also clear, is evidence that the response is broadband with a changing spectrum. And this is with the controller specified with the desired target, with the desired frequency 0.8 and the amplitude 0.5 for the desired target. And we turn on the controllers at around 200 seconds. And then what we're seeing here is once the controller got turned on, and the system very quickly got put under control. And then when it reached the steady state, in a sense, and that is realized as a limit cycle in the first phase portrait on the left, you can see that now the system is basically response-wise follow a well-defined, highly predictable limit cycle. And then the corresponding desired this error, and also got reduced to a level that is considered as negligible. That means the system got put well under control. Let me use these slides to show the control result versus uncontrolled results. This plot is, which is the Poincaré sections of the uncontrolled response. You can see that it's fuzzy, is indicating that this is a highly bifurcated, nonlinear response. The three figures, the rest of the three figures, each correspond to the controlled results following meeting a specific, while also different target signals, okay? And then it indicates that all three control results, they all basically settle down, converge to a limit cycle. What is also interesting, also exciting is this controllers, once it put the systems under control, this Poincaré section, all three of them indicate fractal structure that was very well defined, okay, as is evidence from the three Poincaré sections. All right, the second example that I'd like to share with you quickly is the using the nonlinear time frequency control to control a non-autonomous time-delayed feedback oscillator. This is the feedback this time delay system has rather prominent cubic ordered feedback, as you can see. And then it also has a system level, cubic level nonlinearity as well. So without saying that this is a very difficult system to be controlled. Now using all these parameters, and then we did a simulations. We do the time integrations, and we controlled the uncontrolled system oscillator response with the control results by time frequency controller, as well as the control result by PID control and fuzzy logic control. Okay, and from these time histories of the controlled results, it seems like the system was all put under control. Okay, it seems like at least in the time domain, all well behaved. The response Y is not diverging. It got kept within a set range, right? However, if we take a look at the corresponding phase portrait, okay, you can see that this one corresponds to PID controller, this one fuzzy logic controller, and then this one corresponds to the time frequency controller. You can see that both PID and fuzzy, they indicate high level of non-linearity. The response is highly non-linear. However, time frequency controls result indicates limit cycle. And this shows the corresponding errors. The one on the lower left is the result correspond to PID. On the right correspond to fuzzy. Okay, the errors all very small. So is time frequency controller's error. However, we can see that the errors associated with the PID indicate that even though the error is bounded, but the error actually has high frequency oscillations in it. This is the instantaneous frequency plot for all three control results. Time frequency controllers and shows that the system was properly controlled, and then the system behaved in a way that it follows the desired frequency. However, not so with PID and the fuzzy controllers. Okay, let's start with fuzzy. Fuzzy now, controller now has a system's frequency, this particular mode that is very high. Okay, higher than 130. Okay, and not just that, this temporal model structure indicates that the system was unstable, is highly unstable. As you can see that as the time progresses, its temporal model structures become broadband. All right, and then the corresponding PID's results also has a relatively high frequency indicated in the time frequency plot right here. And this is also not something that was desired, because at least as this frequency, as well as this one with fuzzy, these high frequency mode, they're not indicated, not specified in the control scheme. Okay, so you may ask, how and where did they come from? Well, because let me go back. Because this is a time delayed feedback oscillator. So this time delay and serve as a feedback, serve to perturb, to sway the dynamic state of the oscillators. Okay, and essentially, and then that resulted in the system behaving in a way that is fully undesirable, and then probably totally unexpected. And then with something like this, the system becomes even more difficult to be controlled. All right, the last example is on permanent magnet synchronous motor. Permanent magnet synchronous motor is now very popular. You find it almost in all industry applications, as well as in hybrid and then electric cars as well. And then the popular controlled speed control scheme for controlling the permanent magnet synchronous motor is field-oriented control. So we consider that, and then we implemented nonlinear time frequency controllers into this FOC structures, and then compare it to the FOC PI controlled based FOC scheme, okay, to evaluate the nonlinear time frequency controller against the most popular PI-FOC controllers for comparison. And then we tune these two control schemes the same way to in terms of tuning them in so that the both control scheme can reach the same transient response with the same response time. Okay. All right. Next, let's consider the two cases. The first one is, it's being considered is, now with the motor got subjected to constant load, but changing reference speed, as indicated by this plot right here. So the speed was abruptly switched from positive to negative. And then after 2 seconds, it was switched from negative back to positive. Okay, so the switching is abrupt, it's fast. It creates a significant gradient. Now, the plot on top corresponds to the PI-FOC, and the one below corresponds to nonlinear time frequency FOC scheme. Okay, as you can see that nonlinear time frequency control based control scheme is performed much better than PI based. And then the next is showing you all the corresponding responses from the motor as the control results. As he indicated, let's take a closer look at the subplot B. This corresponds to electromagnetic torque response of the two control scheme. The one on top corresponds to PI. Next, the one below it corresponds to nonlinear time frequency control. You can see that the electromagnetic torque response, okay, as under the control of the PI-FOC, it actually suffered from major oscillation and then delayed in reaching into the target steady state. Okay, and then this also got attested the same. If we look at the tracking error, okay, the PI-FOC suffer from zigzagging in terms of its error. Now, this strongly indicates that systems would undergo significant power consumptions and also significant error in dynamic instability as well. The second case we consider is when the motor is running at constant speed, but this time around with external torque got applied to temporarily disrupt, to perturb the systems. Okay, now, so we can see that the PI-FOC scheme on top restores back to the reference speed at a much faster rate than nonlinear time frequency control FOC. However, high frequency oscillations, as indicated by these two red circles, are observed before the system response eventually settle down to steady state. Okay, so this is a high frequency rippling. When systems is experiencing physically something as such, that means the system is going to hum, is going to make a high frequency pitching, and then also at the same time drawing upon a significant power and trying to overcome this instability. And physically, we're not observing the same thing for with the nonlinear time frequency control FOC. Okay, and now let's take a look at the corresponding tracking error. Right? PI-FOC scheme demonstrate a significant tracking errors, okay, over a range of several seconds, okay, several seconds. And this indicates instability, indicate improper control, but however, not so with nonlinear time frequency control FOC. And I would like to mention that nonlinear time frequency control scheme, once it got incorporated to control permanent magnet synchronous motor, okay, we can use it to achieve both speed and position control at the same time. And all those existing motor control scheme out there cannot do the same. They only they can either do the position control, or they'll have to come up with something different controller to do speed control. No controllers out there can achieve simultaneous same tweaking, same tracking of the position as well as speed control. And then nonlinear time frequency control FOC is fast, is robust, is accurate for controlling this particular permanent magnet synchronous motor. Okay, we didn't just content ourselves with just doing all this modeling simulations. Okay, we actually took the necessary step to set up a experiment to validate the controller design using nonlinear time frequency control concept. And then this is the picture of a very simple setup with the motors sitting right over here, and then the controller is performed through running this simple cheap DSP board. Okay, let me show you, and this is the testing evaluating nonlinear time frequency control against the PI-FOC. Okay, and then we follow what the vendor suggests us to implement both infinite impulse response filters and to the PI-FOC structures. Okay, and then we compared our nonlinear time frequency control results with both PI-FOC results with and without IIR filters. As you can see that nonlinear time frequency controllers control results is actually fast, smooth, without rippling high frequency oscillation, and then the corresponding overshoot is very, very small. Okay, while both PI-FOC control results, they all demonstrate long settling time, very significant prominent overshoot. This right over here with this physical overshoot indicates a sudden high need for high power. Okay, and then If this is too severe, then that could render the motor unstable. Okay, and then this shows the phase A current, the controlled results of the phase A current of the permanent magnet synchronous motor. As you can see that nonlinear time frequency control FOC has had 94% less current overshoot. Okay, this indicates less power consumption and then high level of stability. And this is the case 2. So we are holding the speed constant, but then applied a torque rather abruptly. And more specifically, motor speed was decreased to around 570 RPM by a abruptly applied external torque. And then this torque was very quickly removed. And essentially that is constitute an impact, basically. And then as you can see that from this figure, nonlinear time frequency control FOC handles this impact quite well, but not so with the PI-FOC. These PI-FOC both demonstrate instability, high frequency oscillation in this motor speed. Okay, and then that would also means that the motor requires a much more power to overcome all this oscillation and in this state of instability. And also, as you can see that in this case, without the IR filter, these motors is actually never get to settle down within this time window considered. Okay, again, when we're holding the motor speed constant, and then with this torque suddenly applied and suddenly removed, and then what we're seeing here from our physical data, it shows nonlinear time frequency FOC controller is not only comparable with the PI-FOC, it also restore back to steady state much faster with a much higher level of robustness and stability than the PI-FOC. Okay, so that should conclude my sharing. Thank you very much.